Hello everyone. Let me start by setting the context. The integration of AI in dental prosthetics and orthodontics is part of the larger digital shift. We have transitioned from a traditional workflow where dental models were created using alginate and plaster, requiring meticulous manual labor from prosthetists, to a fully digital process driven by the advent of intraoral scanners. However, to process these scans efficiently, CAD software is essential. These tools enable the 3D printing of digital models. The challenge lies in the fact that scans are often imperfect and not directly printable volumes. Additionally, CAD is increasingly used to better accommodate the clinical and anatomical constraints of patients. For instance, we can now design anatomical bands tailored to a patient's specific dental anatomy, among other prosthetic applications made possible by technological advancements. The first question is, how can AI improve productivity in this process? First and foremost, AI can automate CAD to create digital models and prostheses. It can also optimize the printing phases by intelligently preparing printing trays and improving models to facilitate the patient's treatment. Let's zoom in on CAD automation. First, a scan is a surface, not a volume, and therefore not directly printable. Moreover, raw scans often include many artifacts and are frequently incomplete. Thus, a CAD step is required to model the dentition and, if necessary, create orthodontic or prosthetic elements in dental workflows for subsequent manufacturing via printing or milling machines. For the initial modeling step, specialized dental CAD software uses what is known as an assisted approach. This means that when working with a scan in CAD, users must click on zones that the software will then identify, for example, a tooth. Alternatively, users may draw a boundary with a cursor, after which the software automatically extracts the desired area. But this is assistance, not complete automation. In practice, these assisted detection algorithms require user clicks, followed by geometric approaches to detect contours. These algorithms are fully integrated into today's CAD software to navigate the model and design orthodontic elements. While effective and robust, this process is time-consuming and repetitive for the user. Moreover, it is inherently limited because it relies on a serial workflow. Each case must be completed before moving to the next, as manual intervention is required for every instance. This brings us to the second approach, known as the fully automatic approach. In this case, the manual selection performed in CAD software can be replaced by automatic recognition of zones within the scan. AI enables the software to understand the nature of certain scan areas, for example, identifying a molar without requiring user input. This is known as enriching the scan semantics. With this capability, areas of interest can be directly extracted to generate orthodontic or prosthetic elements using geometric approaches similar to those used in assisted methods today. AI did not emerge in 2022 with ChatGPT. Its history goes much further back. As early as 1950, the Turing test was introduced to determine whether one was interacting with a human or an AI. What is particularly relevant here is machine learning, which appeared in the 1990s. This involves learning from data. We will explore what that means shortly. Today, deep learning, a subset of machine learning, is gaining attention. These algorithms are the bazookas of machine learning, using various methods to reduce the amount of manual data processing and adapt more easily to new data. Within deep learning, we find foundational models for generative AI, such as ChatGPT, which has made these tools accessible to the general public and heightened awareness of their potential. However, these technologies have been implemented in industry for much longer. What do we mean by machine learning? In traditional programming, you solve a problem by implementing a solution with predefined rules written in a programming language. The program processes inputs to produce the expected outputs. That is the classic programming approach. In machine learning, this is not how it works. Instead, an algorithm based on neural networks, somewhat like the human brain, is created to ingest input and output data and autonomously generate the expected results by configuring its networks correctly. Once trained, it can process new inputs to deliver results. This paradigm is incredibly powerful as it shifts from explicitly coding every solution to configuring systems that learn from existing cases. In dental workflows, these software tools work with 3D models. A 3D model is essentially a mathematical representation encoded for computational manipulation. What you see is a mesh, a collection of polygons, typically triangles. It is an array of points connected by edges that form triangles, which together create a surface. A mesh is therefore a surface. So what makes a model printable? Creating a printable model involves transforming a scanned surface, a mesh, into a volume suitable for 3D printing. The first step is defining the area to be used. For example, to create an aligner, only the relevant scan section is needed. AI algorithms are trained to detect the zones to retain for this purpose. Once identified, these areas are converted into a model with supporting structures. This highlights how AI is applied. Training involves using historical data from CAD software experts, enabling AI to predict the zones to retain for aligners, fixed retainers, or other models. Beyond model generation, we delve into understanding the semantics of the oral cavity, a process called segmentation. It follows the same principles as zone detection, but identifies various types of areas, enabling more specific applications. For instance, one might identify a specific tooth type to create custom bands or orthodontic models. The segmentation process involves feeding annotated scans into the AI, allowing it to learn how to identify and categorize different dental zones. This data is then aggregated into an AI model capable of handling new cases. These technologies have numerous applications, including creating whitening trays with customized cups, generating undercuts, filling interdental spaces, or automatically placing articulators. They also allow for direct generation of printable aligners and laser cutting paths. AI segmentation unlocks many orthodontic applications, such as working with worked teeth or generating crowns adapted to the local anatomy. For example, AI can identify scan bodies to generate implant models without manual CAD steps, a major innovation. What are the benefits of this technology? For laboratories, it offers a rapid solution to model creation, with the major advantage of being parallelizable. Whether processing one model, 10, or 1,000, it takes the same amount of time as tasks run concurrently. This significantly frees up time. However, implementing these techniques presents challenges for developers. The processes are complex, especially the geometric parts, as identifying zones within the oral cavity can fail or produce errors. Robust solutions are needed to automate thousands of cases daily. Additionally, processing times must align with laboratory workflows. We have discussed assisted CAD, automatic CAD, and now the future, the pure generative approach. The generative approach eliminates intermediate steps, producing prostheses or orthodontic devices directly from raw scans. Though seemingly far off, this goal is closer than it appears. Generative models adapt to unique cases by being trained on diverse data, including rare anatomies. This removes the need for specific geometric solutions, as the model learns to handle complex cases automatically. Generative AI refers to models capable of producing data similar to their training data. Instead of reproducing what they learn, they create. For instance, ChatGPT generates text based on its training data. Generative AI can also produce audio, video, images, code, and 3D models. It uses randomness to avoid producing identical results every time, and relies on prompts, or input data. For example, a dental scan can guide AI to fill in missing zones, or generate plausible anatomy for gaps. In 3D generative AI, the process involves learning from existing datasets to generate new models. For instance, training on existing chairs enables the AI to create new designs by masking parts of the input, reconstructing them, and iterating until it can generate entire objects. By training on vast datasets, AI becomes capable of generating new, high-quality outputs. Generative AI in 3D is rapidly advancing, with applications across industries. Technologies developed for gaming, cinema, or architecture are often transferable to dentistry. For example, EasyModel uses AI to generate anatomical bands from raw scans. Generative AI can also repair damaged scans, recreate missing parts, and automatically design crowns based on anatomical context. Generative AI also opens doors to more forward-looking research possibilities. For instance, clinical cases could be recorded both before and after fittings. By analyzing thousands of cases, AI could predict and simulate the effects of a fitting, capturing variations across different patients. This approach would provide valuable decision-making support. With a robust database of clinical cases, AI could forecast outcomes based on anatomy, reducing risks. Feedback loops might identify fittings that are poorly adapted or even hazardous for certain patients, enabling adjustments to be made proactively. The foundation of this approach lies in leveraging feedback loops between practitioners and laboratories. Rather than replacing expertise, AI augments it by synthesizing past exchanges to propose more tailored initial solutions. The goal is to support experts in decision-making without ever substituting their critical judgment. One of the most significant advantages of generative AI is its multimodal nature. Alongside 3D scans, it can incorporate practitioners' instructions and other data sources to anticipate treatment outcomes more effectively. For example, when scans fail to reveal certain elements like roots or bone-embedded teeth, complementary data such as CBT scans can fill the gaps. Generative 3D AI faces challenges such as handling large datasets, ensuring structural quality, and addressing errors like hallucinations. Post-processing is often required to refine outputs for clinical or laboratory use. Additionally, training generative models is data-intensive and costly, especially in healthcare, where data expertise is critical. AI is a transformative tool for laboratories, enabling parallel workflows and freeing staff for higher-value tasks. While solutions based on automatic approaches are already available, generative 3D AI is emerging as a powerful complement with vast potential. To remain competitive and unlock the full potential of these technologies, laboratories should adopt AI tools now, paving the way for more advanced, tailored models that surpass traditional CAD limitations. As automation increases, it is vital to consider evolving regulations, such as the AI Act and medical device standards. Tools for validating AI-generated results will also be essential. Finally, interfaces must evolve to be more intuitive, incorporating modalities like voice control. Multimodal tools will play a key role in shaping the future of AI in dentistry. Thank you for your attention. I hope this webinar has given you a better understanding of AI techniques. If you have any questions, please do not hesitate to contact us. Our teams will be delighted to answer your questions and explore your challenges. We wish you a great day and see you soon.